Hello viewer, welcome again to Samuel Academy. In this video, I will explain Hooke's law. Now Hooke's law describes the behavior of elastic materials. In this law, we find that the force that is needed to stretch or compress a spring is directly proportional to the change in length of the spring from its equilibrium position as long as the elastic limit is not exceeded. So we can express this law in the following way mathematically, that F, which is force or load, is directly proportional to X, where X is the change in length or extension. And so if F is directly proportional to X, it implies that the force F is equal to Kx, where K is a constant. So K is the spring constant, which is defined as the force per unit extension in newtons per meter. Let's continue. Now, in this case, we want to investigate Hooke's law using a helical spring. Now, this is the helical spring. Its length is L. From here to it is L. And then, when a force or a load is exerted on this spring, it stretches. There is an extension. There is a change in length. So you can see this spring is now longer than this one here. So this is the measure of extension, X. Okay. So we want to see how we can determine that relationship, that force is equal to Kx. So in this case, we do an experiment. Okay, we put the force or the load, we exert a force on this spring different times using different masses, and then we record the change in length in a table. So we have this table. The first column are the masses which we hang on that spring. Here in the first case, there's nothing. Then 10 grams, 20 grams, 30 grams, like that. Then we shall change this mass into kilograms. Like 10 grams, we change into kilograms, which is 0.01 kilograms. And then we change that mass in kilograms into newtons, right? Because force is equal to weight. From this expression, F is equal to ma. Force, F is equal to mass times acceleration. In this particular case, acceleration is g, the acceleration due to gravity. So the weight is equal to mass times acceleration. So 0.01 kilograms times 10 newtons per kilogram, because G is approximately equal to 10 newtons per kilogram. So multiplying this by this, you get 0.1 newtons. All right. So we have 10 grams into kilograms into newtons, it is 0.1, like that. Then we record the spring length in centimeters. Initially it was 20 centimeters. Then it stretches to 25 centimeters, 30 centimeters, like that. Then in this last column, we calculate the extension. Here it is 0, because there's no extension here, there's no force applied. Here it is 25 centimeters minus 20, we get 5 centimeters. 30 minus 20, you get it 10. that 5 minus 20, you get 15, like that. So this is the extension in centimeters. Now these extensions in centimeters, we shall change into meters by dividing by 100, right? After that, we draw a graph, the force extension graph, whereby on the y-axis we have the force in newtons, that is the weight, and on the x-axis we have the extension in meters. So when we plot this graph, we get this line graph, right, which is a straight line up to the elastic limit. All right. Beyond that, we find that this graph does not conform to Hooke's law because it is beyond the elastic limit here. Now, from this graph, we can determine the spring constant K. How do we do that? We find the gradient, the slope of this line. That is the change in y over the change in x, dy dx. All right, in this particular case, change in y is equal to 0.4 newtons minus 0.1 newtons, right? Divided by change in x is 0.2 meters here, subtract 0.05 meters. So you get 0.3 divided by 0.15, you get 2 newtons per meter. So 2 newtons per meter is the spring constant for the force extension graph. Let's see when we plot the extension force graph, what happens. So this is the extension force graph. On the y-axis, you plot the extensions in meters. On the x-axis, you plot the force in newtons. So this is the graph you get here up to the elastic limit. All right. Then if you get the gradient of this graph, we find that this gradient is equal to 1 over the spring constant, 1 over k. All right, which is found by getting the change in y dy and change in x dx. So that is 1 out of k. All right, from here we get change in y is equal to the change in extension, that is 0.2 here, minus 0.05. This is what I'm doing. Divided by the change in x, which is 0.4 newtons minus 0.1 newtons. So you get 0.15 divided by 0.3, you get 0.5 meters per newton. Okay, so you see in the first case, in the force extension graph, the spring constant was 2 newtons per meter, but this is 0.5. That is 1 out of the gradient. 1 out of k, the spring constant, you get 1 divided by 2, you get 0.5 meters per newton. So that is how we can investigate Hooke's law using helical spring, by drawing the two graphs, taking measurements and drawing the two graphs. So we have seen the relationship. Now, if we find this video useful, please subscribe for more videos in chemistry, physics, geography, weather and surveying in my channel. Thank you so much.